So another semiconductor device, the bipolar junction transistors. It consists of two PN junction diodes. So BJT was formed by two PN junctions, P, N, P. Or N, P, N. Okay, bipolar. So bipolar junction transistor, simply we term it as BJT. BJT is a current control device. Okay, why? Because if you apply some input voltage, we get the output current. Okay, so the reason why the BJT is called current control device. So further we will study voltage controlled devices like MOSFET field effect transistors, current controlled device. Whereas field effect transistors are voltage controlled devices. Voltage controlled devices. Voltage controlled devices. Okay. So coming, we'll discuss only BJT, bipolar junction transistor. So it is a current control device. We need to remember this point. Okay. Now, how the PNP or NPN transistors are formed? We know how the PN junction diode is formed, how the junction is formed. Okay, so in the formation of bipolar junction transistors, generally there are three terminals called emitter, base, collector. These are the three terminals. So emitter, base, and collector. Generally, emitter is the thick region when compared to base region. Base is very thin, small in size, thin region. This is moderately doped material. If it is a NPN transistor, emitter is N-type material. In region, this is lightly doped. If it is NPN, base is the P-type material, lightly doped material. And this is also thick region when compared to both emitter and base. The collector region is larger in size. So this is also thick region when compared to both emitter and base. So this is somewhat heavily doped. Heavily doped. Heavily doped and larger in size. So these are the three junctions of a bipolar junction transistor. So whenever we are drawing the PNP or NPN transistors, so base, we need to remember that base is smaller in size. So correct representation is, if you represent a BJT, this is the emitter region. Emitter. This is the base region. This is the collector region. So in this diagram, we can understood that the emitter is somewhat thick compared to base region. Base is very much smaller region when compared to emitter and base. Collector is larger region when compared to emitter and base. So this is a correct representation. This collector, base. These are the three terminals of a transistor. So transistor is a three-terminal device, whereas diode, Zener diode, PN diode, okay, several other special diodes are there. All are two-terminal devices. Okay. So this is a three-terminal device. Coming to the symbol of BJT. So if you consider the BJT symbol, this is the base region, this is collector terminal, and this is emitter terminal. This arrowhead represents this is NPN transistor. NPN transistor. Okay, NPN transistor. Coming to the symbol of PNP transistor. This is the base region. This is the collector, emitter, terminal. So this is the PNP transistor. How to differentiate these two transistors means only with the help of this arrowhead. Okay, if the arrow is towards the base junction, that will be PNP transistor. If the arrowhead is away from the base junction, that will be PNP transistor. Sorry, this is NPN transistor. Okay, so understood the symbol. So coming to the BJT bipolar junction transistor is used as an amplifier, okay, in the electronic circuits, and we can use the transistors in the oscillator and power amplifiers, many applications. When compared to diodes, the bipolar junction transistors have large number of applications. So in the integrated circuits also we have these transistors. Millions of transistors can be accumulated in a single chip. So this is a symbol. Coming to the configurations. So how many junctions are there in the BJT? Only two junctions. Says one. Only two junctions are there. How many configurations means three. This is N, P, N. NPN transistor. How many junctions are there? Junction means P to N, PN. This is the junction. This is the junction 1. This is the junction 2. So in a BJT, how many junctions are there? Only two junctions. Okay. So how many configurations means? Those are three. How it is means? The BJT can be operated in three configurations. Bipolar junction transistor can be operated in three configurations. One is common base configuration. CB, shortly we'll call it as CB configuration. Common emitter. So as the name suggests, common. Common means it is common in between the input and output. The terminal which is common in between input and output is called common. So common collector. As this is 3-terminal device, we have 3 configurations. Okay, these are the BJT configurations: common base, common emitter, common collector. So let us discuss these 3 configurations. So first one, common base configuration. Let us we have understood what do you mean by common base. So CB configuration of transistor. So first we'll draw the configuration. Okay, let us draw the circuit diagram. So this is the emitter terminal. The arrowhead represents emitter. This is base. This is collector. This is emitter. So emitter is considered as the input in the common emitter, common base configuration. So common means the base is connected to ground. So this is a common base configuration of the transistor. Okay. So, in the study, we'll see biasing also. So biasing means we know connecting external DC voltage. So in the common base configuration, what is the input? Input side is input is connected to the emitter region, emitter and base. This VEB is called input voltage. Input voltage. This current. So current generally flows like this. This is emitter current. And this is the base current. N region. So current flows like this. So these are the currents. So output current is collector current. Output voltage is VCB. VCB is the output voltage. So how we have connected this battery or the external DC voltage? Always remember in the BJT, bipolar junction transistor, in all the 3 configurations, whatever the configuration, emitter to base should be forward biased. Emitter to base should be forward biased. Forward biased. So we know what do you mean by the biasing, as in the PN junction diode we are seeing. Emitter to base should be forward biased. Collector to base should be reverse biased. Collector to base should be reverse biased. So what are these conditions? If you operate this like this, the transistor will be in the active region. Transistor is in active region. There are 3 regions called cutoff region. See once. So when the transistor is said to be in the cutoff region, cutoff, active, saturated, saturation region. Based on this external DC voltage only, the transistor will be in the collector to base. will be in the cutoff region or active region or saturation region. When the transistor is said to be in the cutoff region means, cutoff means off state. So when it is in the off state means when emitter to base is reverse bias, collector to base is also reverse bias. Then transistor is said to be in off state or cutoff region. When the transistor is in the active region means emitter to base is forward biased, collector to base is reverse biased. When the emitter to base is in the forward bias and collector to base also in the forward bias, then the transistor will be in the saturation region. Saturation region. Both are forward, then saturation. Both are reverse, then cutoff region. When the transistor is said to be in the active region means when emitter to base is connected to forward biased and collector to base is connected in reverse bias. Now let us see whether this common base configuration is connected in active region or not. See, this one emitter. Let us consider this transistor is NPN transistor. NPN transistor. Then only this is in the active region. See this one. Emitter is N region connected to negative terminal of the battery. So emitter is N is connected to emitter, N type material. Okay, negative terminal is connected to N region and positive terminal is connected to base region. So here base is P type. So positive is connected to positive. So emitter to base is said to be forward biased. Similarly, collector to base. So collector terminal is N type material. So this N type material is connected to positive terminal of the battery and base is P type material connected to negative terminal of the battery. So collector to base is said to be in the reverse bias. The reverse bias. So in the common base configuration, we need to apply the external DC voltage like this. Then only transistor is said to be in the active region. Now from this diagram, we can see the currents relation also. So emitter current is towards the transistor emitter region and we will apply. You will consider this entire transistor is a node and emitter is towards the junction. Let us consider this is positive. Collector current is away from the junction. Consider this as negative. And base is also away from the junction. So consider this as negative. So the algebraic sum of currents at a junction is equal to 0 according to the Kirchhoff current law. So what is the current relationship in the common base configuration or in any configuration? This is true. This is the transistor BJT current relationship. Emitter current is equal to the sum of collector current plus base current. Okay. So coming to the in the CB configuration, if the transistor acts as an amplifier, then what is the current gain? What is the current gain or current amplification factor? In the common base configuration, current amplification factor is defined as alpha. And here the alpha is nothing but current gain means in the common base configuration, output current is IC. So IC divided by input current is IE. Input current is IE. So the definition for alpha is it is the ratio of output current divided by input current. Nothing but IC by IE. Okay. So what about this IC by IE? The range of alpha. Range of alpha is less than 1 and it ranges from 0.95 to 0.995. Okay. So this is the range of alpha. Okay. It's called current gain. And coming to the common emitter configuration. CE configuration. So in the common emitter configuration, the emitter is connected to ground. So we'll draw the transistors like this. So here also we are considering NPN transistor. Base region. Okay, see this one. Here the base is connected to positive terminal of the battery and emitter is connected to negative terminal of the battery. Now see this one, as this is NPN transistor. So base is P-type material. So emitter is N-type connected to negative terminal of the battery and base is P-type. This is connected to positive terminal of the battery. So emitter to base is said to be forward biased. Emitter to base is said to be forward biased. So this is the input current, base current. Due to the positive terminal, current flows in this direction. The emitter current flows in this direction. And as this is positive terminal, current will flows like this. This is the collector current. Now, if you see the current relationship, the emitter current is away from the node junction or from the BJT. If you consider entire BJT as a single node, so emitter is away from the node and base current is flowing towards the node and collector current also flowing towards the node. So this equation is true for all the three configurations. No need to verify. Six. Okay. Now this output voltage is nothing but VCE. So input current is IB, output current is IC. So in the common emitter configuration, what is the current gain? What is the current gain? The common emitter configuration is current gain or current amplification factor. Both are same. Current gain in CE configuration is given by beta. So here beta is given by output current is collector current, input current is base current. Okay. So this is IC by IB. So what is the range of this beta is? Beta generally ranges from 20 to 500. 20 to 500. So in the laboratory experiment or education purpose, we use BC 107 or 108. 107 is the NPN transistor, 108 is the PNP transistor. So for BC 107, the current gain in CE configuration is 49. Okay, it's the range. So 20 to 500 general range. Where we use this much of gain means in the power amplifiers. The cost also proportionately increases as the gain is more. So this is beta. We know the relation IE is equal to IC plus IB. So we can determine what is the relationship between alpha and beta. Relation between alpha and beta. So if we divide with the IC on both sides, IC on both sides, what we'll get? IE divided by IC equal to IC by IC, that is 1, plus IB by IC. Now, what we'll get? What is IE by IC? IE by IC is nothing but 1 by alpha. See the relation. IE by IC. IE divided by IC is nothing but 1 by alpha. This is 1 by alpha. So IC by IC, this is 1 plus C is 1, IB by IC. See here, this relation. IB by IC is nothing but 1 by beta. This is the relationship between alpha and beta. Okay, this we can easily remember. 1 by alpha is equal to 1 plus 1 by beta. Or if you express alpha in terms of beta, what we'll get? Okay, take the LCM. 1 by alpha is equal to 1 plus beta divided by beta. That implies, what is the alpha here? Alpha is beta divided by 1 plus beta. Beta divided by 1 plus beta. Okay. Similarly, if you want beta, so what we can do? 1 by alpha, rearrange this equation. 1 by alpha minus 1 is equal to 1 by beta. Now take the LCM. 1 minus alpha divided by alpha equal to 1 by beta. Now from this, we can express beta in terms of alpha also. So that is beta equal to alpha divided by 1 minus alpha. So this is how we can easily remember the relationship. So if you remember this, this is fine. Or otherwise, alpha is always less than 1. So beta is greater than 1. In this way also you can remember. Beta, for example, this is 10 divided by 1 plus 10. 10 divided by 11 is always less than 1. So beta is equal to alpha is, for example, consider this as 0.9. 0.9 divided by 0.9 divided by, we may have confusion, 1 plus alpha or 1 minus alpha. If you check like this, we can easily remember 0.9 divided by 1 plus 0.9 becomes, this beta will be less than 1. Beta will be less than 1. So what we need to remember? 1 minus alpha. So if it is 0.9 divided by 1 minus 0.9, then this will be 0.1. So this point and point gets cancelled. Beta becomes 9. Okay. So general example. Generally alpha ranges from 0.95 to 995. If you substitute 95, then we can get beta more than 20. Okay. So this is a relationship between alpha and beta. So very simple to remember and very important also in solving the problems. Now coming to the common collector configuration. Common collector configuration. CC. So how to connect the common collector configuration means the transistor will be connected like this. So collector is connected to ground. Collector terminal is connected to ground. So base terminal acts as the input and just will simply reverse the terminals. So this is the collector terminal. It is connected to ground and here is the base. So base is acts as the input. Let us check the polarity data. So this is the emitter junction. See the if it is NPN transistor. N, P, N. This is the base region, emitter region, collector region. So this is P-type material. So P is connected to P. Collector to base. Collector to base should be reverse bias. So here the terminals are wrong. Collector to base should be reverse bias. Always we need to follow this condition to make the transistor is operated in active region. So collector is N-type material. So we need to connect to positive terminal like this. So base is connected to negative terminal. No issue. And now see this one. N-type material. Emitter to base should be forward biased. So this will be connected to negative terminal as N is connected to negative terminal. So like this, we can remember the biasing of the transistor. Now this is collector terminal directly connected to the ground. Now see the polarity of the currents. Okay, as this is emitter terminal is connected to negative region. So current always flows in this direction away from the junction. So here also away from the junction. Here emitter is away. So base is towards the junction. Collector also towards the junction. Okay, this is how we need to remember. So that emitter current IE is always IC plus IB. IC plus IB. Okay. So in the common collector configuration, what is the current amplification factor? What is the input current here? IB. IB is the input current. IE is the output current. Okay. So collector is common. So current amplification factor or current gain in the CC configuration. Current gain in CC configuration is represented as gamma. Okay. So what is gamma is output current is the emitter current divided by input current. Input current is base current. Okay. So if you want the relationship, the gamma also ranges like beta. So this also 22,500. Okay, greater than 1. Gamma is greater than 1, like beta. If you see the relationship, so that we can have the value of the range also. So always we'll take the current relationship. IE is IC plus IB. IC plus IB. So if you want gamma, so what we need to do, gamma is IE by IB. So divide with IB on both sides. Divide with IB on both sides. So what we'll get? IE by IB. IE by IB is equal to IC by IB plus IB by IB is 1. Okay. So now we know IE by IB is nothing but gamma. IB by IE by IB is gamma. And IC by IB. IC by IB, where we have seen, see this one. What is beta? IC by IB. So here we'll write beta. So this is written as beta plus 1. Now we can have the relationship between gamma and beta. What is the relation? Gamma is equal to 1 plus beta. Gamma is 1 plus beta. So if you want the relationship between gamma and alpha, what is beta in terms of alpha? Alpha by 1 minus alpha. Alpha by 1 minus alpha is the beta plus 1. So what is gamma in terms of alpha? Alpha plus 1 minus alpha divided by 1 minus alpha. So finally, what is gamma in terms of alpha is gamma is equal to, say, plus minus cancel. Gamma is equal to 1 by 1 minus alpha. Gamma in terms of beta is gamma is equal to 1 plus beta. Okay. So this is these relations are very important while solving. These are the interrelationships. So if you have one of the parameter, we can find other current gain factors. Okay. Alpha is the current gain in CB configuration. Beta is current gain in CE configuration. Gamma is current gain in CC configuration. Okay. So this is about the configurations. Transistors can be operated in 3 different configurations. Among these configurations, most likely used configuration is CE configuration due to its advantages. Okay, advantages. What are the advantages when we compared the advantages? So current gain in the common base is less than 1, so no use. This is greater than 1, so somewhat amplification will be done. This is also greater than 1, but stability is less. The stability is less in the common collector configuration. So high gain is produced, but stability is less. So CC configuration generally used in oscillators, and CE configuration is used in amplifiers. CB configuration is generally gain is less than 1. We cannot use it as amplifier. Some clipping and clamping circuits will use the common base configuration. Okay, you'll study the applications also. So most commonly used configuration of transistor is CE configuration. Generally, if you purchase any transistor also, they mention beta value also, beta value. Okay, like a specification they will give. So this is the so and so transistor. Its beta is this one. Okay. Why they mention beta only means generally we use the transistor is in CE configuration for amplification. Okay. Most commonly used application is amplifiers. Okay. So this is about the transistor types NPN and PNP transistor and configurations we have discussed.